Hello everyone. Today we'll be looking at an interesting combinatorial problem from the IMO team selection test. So this says that a snake of length k is an animal which occupies an ordered k tuple of cells in an n cross n grid of square unit cells. So now what is this saying? They go into some of the actual definitions of what these cells are and how you define the snake and so on, but we don't actually need to do that because we can just get an intuitive sense of what a snake is. So a snake is in nothing but some animal of length k that lives inside the grid. It has a head and it can only move inside the square unit cells. So it can move from one cell to the other. It can slither like this, but its head will actually recede. A tail will actually recede in the process. So and it can move around in all kinds of ways, all while the tail is receding. So now we say that now it can also never intersect itself. That's another rule. So now we say that the snake can turn around if it occupies some set of cells in the beginning but after a finite number of moves occupies the same cells but in reverse order. So this is nothing but saying that initially what was the head, the square cell that was the head has become the tail, and the square cell that was the tail has become the head, but the pattern of the snake is exactly the same. So now we need to determine whether there exists an integer such that we can place some snake of length at least 0.9 n squared in an n cross n grid which can turn around. So now let me explain the difficulty of this. Now an n cross n grid, 0.9 n square is pretty close to the actual area of the grid. So we need to place some snake in. It's very close to the area of the grid, but it somehow manages to use the few cells which are not covered, the 0.1 n square cells, in some way such that it can maneuver to turn its head into a tail and its tail into a head. So the question is, how do we do this? So I'm going to use, for illustration purposes, a 12 cross 12 grid, but note that this will actually not work for a 12 cross 12 grid. We actually need a much larger even integer. So, and we'll get into that in the end of the video. But I'm going to just use this to show you how the construction actually works. So firstly, we omit the first two rows and the first two columns, the last two rows and the last two columns of the grid, and we create this frame, this n-4 cross n-4 frame. And inside this frame, we place a snake exactly as shown in the figure. It has some length, which is n-4 cross n-4 the whole square, and it covers that entire area, and it is placed in this zigzag manner, such that tail, and this marked in red is the head. So snake, we claim, can turn around after some finite number of moves. So how are we going to do this? Well, the first thing we're going to do is make the snake go down all the way like this, and then go up all the way like this, and then go around, and then start moving around here. So this is illustrated in the next figure. So it has gone all the way around, it's gone like this, and is now zigzagging here. But now, after the first zigzag, it actually moves to the side by one step, right? So what it does is it moves like this, one step to the side, out of the frame, and it goes inside, and it leaves one entire column unoccupied inside the frame. So this here, it makes this pattern continuously like this, until you end up with nothing but this. So it's the same kind of snake, but it's been reflected, even though what we want is a rotation, but it's been reflected such that the head, which was facing this way, is now facing this way. It's also translated by 1 unit to the left and 1 unit down. And now we can maneuver the snake as follows. We can make it move like this, like this, like this, all the way around, and make it go like this. So this goes all the way like this, and we make it go all the way around. So it goes all the way around as such. So it moves like this now inside the grid, and as you can see, the head is now very close to the tail. So all the snake needs to do now is to follow the tail closely. So the snake does this. It follows the tail, it goes inside, it follows the tail as the tail keeps receding, and there's a distance of 2 or 3 cells. The exact number doesn't matter, but there's some distance between the tail and the head, and as the snake keeps moving, the tail will keep receding. So if the tail recedes, let's say recedes somewhere here, then the snake actually goes into the grid and starts zigzagging again. So this is shown like here. So it goes inside the grid, and now it'll start zigzagging again, and it keeps zigzagging all the way until it reaches here. And now what we can do is we can actually bring the snake down like this and have it start zigzagging here. And now if it zigzags here, if you follow the movements, the head actually ends up exactly here. So just like that, we have turned around the snake. Is that if we take n as some very large even integer, the limit as n goes to infinity of n minus 4 the whole square by n square, which is the area, goes to 1. So if we take n to be sufficiently large, we can actually do the same series of moves. So this is possible because the sides of the grid allow us to maneuver the snake in this very particular way. So now all we need to do is generalize this for some very large n, and we are done. So in fact, the constant 0.9 was arbitrary. It could have been 0.99, it could have been 0.99999, and so on. It could have been anything that is less than 1. So it could have been anything less than 1, and yeah, so just like that, we can turn around a snake of at least length 0.9 n square. So that's all for today. Thank you for watching, and I'll see you next time.